Hi, Rafael.
Hi, I can only see Alexander, but sorry, I may need to. I don't know.
If you this about gallery.
Okay, here I am. Okay, hi, Emilian. Nice to see you.
How are you? Okay.
Yes, fine, thanks.
Good to see you online at least.
Yeah, well, I'm sorry, I'm not there in person, but
Okay.
maybe it's
Yeah,
well, it's a bit of a tricky situation now.
yeah.
Maybe we'll see you at BMC if you're coming.
Yes, yes, I should be there.
Okay.
This is the intention.
Actually Alberto Rafael considered very seriously to come to us in person, but then closer to the seminar, it's because the situation didn't improve well, and so it was the kind of dangerous in some sense to come. So by the way, our speakers, some of them, they very keen to come, and so they ask to move them to May. So hopefully in the May it will be better. But before the Easter, at least Mark Bly will give seminar in person. I hope. Yeah. Right. So it's already time, and we all participants, I hope, is there. Yeah, and our seminar today will be given by Rafael Stuhlmeier. I believe it's a right pronunciation.
Yes,
Stuhlmeier
absolutely.
from Plymouth. It's about wave forecasting, which will be about nonlinear waves mainly, as I understand. Is it?
Well, we'll get to the nonlinear waves
Yeah.
soon.
Okay. And then I had a talk to Rafael before, and he said it's okay if all of our participants, switch off camera. So then the drawback is that our speaker couldn't see the room, could see us, but Rafael said that he is teaching like that to the black screen already for 2 years, so it's not surprise for him. So then, but for us, it's good to switch off the camera and mute microphones. I see that all participants muted their microphones because then the quality of seminar would be not quality of seminar, quality of connection, internet would be slightly better. So Rafael, please start your presentation, and could you please introduce a little bit yourself, because something from your story was a surprise even for me today.
Okay, I won't. Thank you very much for the opportunity to talk here and for the nice introduction. And again, I'm sorry that I can't be there with you in person today, but I hope to be back in Norwich again soon. So please, if there's if the connection cuts out or something, please do feel free to interrupt at any point. If you can't hear me or understand what I'm saying, I'm hoping that everything it will be under control, but you never know these days. I won't say too much about myself, except that I'm based at the University of Plymouth currently, and some of the work that I'm presenting is joint with Miki Stiasny from the Technion. And lately, so another paper is joint with Mariano Galvano, who's a visiting researcher here in Plymouth, and Debbie Aeltink, who is at Oxford and now in MIT. So with two groups in engineering there. So the title of the talk is Weakly Nonlinear Theory for Deterministic Wave Forecasting. And I want to start with the big letters, namely deterministic wave forecasting, and in particular with wave forecasting, because I saw the other seminars that are taking place this year or this semester at UEA, and I see not everybody is in fluids, not everybody is in water waves. So I'll start from the beginning, and then we'll work our way, hopefully, into something interesting. So wave forecasting, first off, started mostly because of scenarios like this. Around the Second World War, the Allies, so chiefly the Americans, were having to fight on lots of beaches. So they were trying to reclaim lots of beachheads that they had lost or that they were struggling over, mostly in the Pacific, but also in other theaters of war. And one of the problems was ferrying soldiers onto the land. So it became clear that since these ships, these small transport craft, aren't very seaworthy, it's important that the wave conditions be correctly forecasted. Otherwise, the whole logistics of an operation might go awry. And they gave this problem to Sverdrup and Munk in 1942. And Sverdrup and Munk attacked it, well, essentially by looking at how to forecast waves. And we know waves are generally generated by the wind. And the wind is generated by pressure differences in the atmosphere. So this is yesterday's weather. So I didn't update it this morning, but it's still more or less accurate, I think. So we know that the wind, by and large, goes along the isobars, and that this blowing wind generates waves. So if you have a mechanism for how the wind generates the waves, and then you say how the waves propagate, then you can do some forecasting. And the kind of forecasting methodology that Sverdrup and Munk developed was refined and refined over the last 60, 70 years, and is still used today. So here I'm showing you an animation. So this is the low that we're currently experiencing today, and it's moving a little bit to the east. This is actually a live forecast. You see the isobars here in white, and the little white lines that are propagating here, those are wave fronts. So this is from so this animation is from a modern wave forecasting tool, where the wind wind input to the ocean is used to give averaged characteristics of the sea state. So in this picture, the colors, so darker red means higher average sea state, and lighter blue means a lower averaged sea state or lower averaged wave height. And correspondingly, you can say some things about the average periods as well. So these kinds of forecasts are very, very useful. Averaged information is great when you're building a seawall. For example, you'd like to know if average storms are doing this or that, how high should the seawall be if it needs to survive for a year or 2 years or 5 or 10 or 50 years. Averaged numbers are also great if you're thinking about what the deck height of your offshore platform should be. You don't want to build it too high because each additional meter might cost you 50 million pounds. You don't want to build it too low because, well, maybe one of those storms will get there. So averaged information is very, very useful. It's also good when you're thinking about where to place wave energy converters, as you can see in this kind of cartoon diagram. So here's some yellow floating buoys, and there's a substation, and these buoys are supposed to oscillate up and down and generate energy. Of course, you want to put them in an area with high average energy. But sometimes average information isn't sufficient, and wave energy, in fact, provides one such case. You can think about a system of wave energy converters like this, so with buoys bobbing up and down. And of course, once the geometry of the buoys is set, there's not much that you can do about it. There's a certain damping that you can use to control the motion of the buoy. But aside from that, well, this buoy has to do well when the sea is calm and when the sea is very rough. And what people have appreciated for quite some time, so in the wave energy community for, let's say, about 20 years now, is that if you can use some automatic control for these buoys by adjusting the damping parameters to the incident sea state, you can start to capture much more energy. So the bandwidth at which you can capture energy becomes much broader. The caveat is that you need to know what waves are coming. If you know there's a big wave, well, you need to adjust your damping coefficient. If there's a small wave, well, you need to adjust it too. So you need some kind of prediction, and not just average prediction, but actual phase resolved prediction that tells you in a minute or in 10 seconds or 5 seconds what wave is going to arrive at the buoy. There are other situations, and I'll play this video, where, again, it's clear this ship is doing, having a difficult task in these sea states that are quite rough. So significant wave height is quite high, but this helicopter, which is courageously trying to land, isn't so worried about the average sea state. It's worried about specifically what waves are coming. How is the ship heaving and rolling and pitching in these waves? So in the scenario that you see here, and I don't know anything about the veracity of the video, so please don't ask for details. It looks very dramatic. In the scenario that you see here, the pilot is able to use some, presumably good instincts to find a quiescent period where the roll and the pitch of the ship are manageable, and he's able to land this helicopter. But if you think about trying to do such operations autonomously, say via drones or with other autonomous systems, it's clear that providing some phase-resolved information about waves or what waves are coming can be very useful. So this is the why of deterministic wave forecasting. Why is it interesting? Because you can start to improve lots of different systems that actually operate in the sea and in the ocean. So now on to the how. And I'm going to start, well, with a very, very simplest ideas. And this is really how we started out trying to understand the problem ourselves when we tried to tackle it. So let's say I know what the sea state is now. I've got a picture of the sea. In this case, it's at a single time and over a spatial record of 1,000 meters. How can I predict where the waves are going to be? Well, let me discretize this wave record, length L, say. I've got a series of points, and then I can extract Fourier modes from this using the, say, the FFT, which is quite efficient, as everybody knows. Now, if my record were composed of sinusoids with modes between, say, 1 and the whatever the highest mode is, then I'd be completely in business. The Fourier transform, discrete Fourier transform given here, so yn are the original signal, so that's the original signal, the sampled points. The capital Yj's are the Fourier amplitudes, and I can construct a continuous and periodic extension of the original signal just by replacing a discrete variable with a continuous x. So if my C were composed of sinusoids, this would be an accurate representation of that C. And moreover, if the C were composed of sinusoids, I'd know how those sinusoids propagate in time and in space. Because, well, the water wave problem, the linear water wave problem, has a solution in terms of these harmonic waves. So a wave with wave number km has a frequency, in deep water at least, of omega is square root of g norm km. And then I can put that together into a linear forecast. Effectively, I've taken my FFT, my discretized signal, I've added a sprinkling of linear dispersion, and I have a linear forecast where the first term that doesn't have a harmonic wave in front of it is a sample mean, like the mean sea level. And so you can just draw a squiggly line, and if your squiggly line behaved like linear waves behave, you can let it rip. You can let things propagate, and this is effectively linear dispersion on a squiggly line. So, of course, what's the squiggly line? How good is this? And so on. All of these are the questions that we need to address. So, first things first. And again, I hope the experts will forgive me, but just for everybody not in fluids, I want to emphasize in water waves are dispersive, and group velocity and phase velocity are distinct. The phase velocity, namely the velocity of a crest given by the red dot here, is distinct from the group velocity given by the blue dot. And the latter, namely the group velocity, is the velocity at which energy propagates. What we need to be tracking when we look at how good a forecast is, isn't the velocity of each wave crest, but it's the velocity of the envelope or the velocity of the energy. And this idea gives rise to a theoretical concept, which again, it's not, we didn't invent this, but it's a theoretical concept called the predictable region. So let's talk through the diagram. On the horizontal axis, I have x, so space, and in the vertical axis, I have time, t. At time t equals 0, I assume that we have a wave record of right-going waves only. Okay. I can talk later on about the ambiguity if you've got right and left going waves. This is, of course, a problem when you do Fourier analysis. But let's assume, since everything is unidirectional now, all of our waves are right going. If I have a record, say a picture of the free surface at time t equals 0, wherever I look into that record using Fourier analysis, I'm going to find modes. Say I look at this point x0. I'm going to find modes between the very longest, which are modes wave number k0, to the very shortest, wave number kn. The longest waves, because of the dispersion relation, will travel fastest. They'll travel along these rays. Notice these are rays that are whose slope is proportional to the reciprocal of the group velocity. So along these rays, and the shortest waves will travel along these rays here. So that thick line. What that means is that if I start with a measurement between x0 and x1, the energy of modes between k0 and kn, will be in this shaded triangle. Outside of the triangle, I'm losing information about waves that originated in the domain of my picture. So this gives us a predictable region in which we can hope to forecast. Okay, outside of it, there's nothing that we can say theoretically, except, well, in very partial results about, say, longer or shorter waves than the waves that are in our record. Okay, so the predictable region constrains in space and in time the kind of forecasts that I can make if I want to make those phase-resolved forecasts I was talking about. And to give you an idea of how big that region is, I've provided here a synthetic spectrum. So this is like the average of many, many Fourier spectra for typical Cs whose wavelengths are around 90 meters and significant wave heights, that's that averaged characteristic, is around 5 meters. Most of the energy is contained between the waves that are around 20 to 200 meters long. And those are the energy of those waves is between 3 and 9 meters per second. So it's propagating with group velocities between 3 and 9 meters per second. And the triangle that I showed you, if I sample over 1,000 meters, then the apex of it is at around 160 seconds. So this gives you an idea that the scales that we're working on with deterministic forecasting are very modest. The sampling, if you're concerned at all, there is, of course, technology to do this, such as X-band radar. You can use LiDAR. You can think about using spotter buoys and other things. But the sampling around 1 kilometer or that type of scale is very much realistic. So we're not talking about huge swaths of the open ocean that we're sampling. So now that we know where the prediction might work, of course, the next natural question is this linear prediction any good? So hopefully the answer is no. Otherwise, the talk is over and you can, well, maybe that's good news. You can all enjoy the rest of the afternoon. But I'll tell you how this is measured, or how we measured it in this case. So what you see here in this graph is an averaged correlation. Correlation, just a linear correlation measuring whether two signals rise and fall at the same time. So if the correlation is 1, they rise and fall together. If it's -1, one rises while the other falls. 0 is then there's no correlation on average. So the first thing that we need to do is to generate a C state. And in this case, I've done that using higher order spectral method, which is a sophisticated nonlinear computational method to generate very realistic C states. So I initialize a C state, and I've done that for 3 values of steepness. Not so steep is epsilon 0.1, medium steepness, and fairly steep is epsilon 0.2. And I've done it for an ensemble of 50 realizations with random phases so that I'm not bound to what's going on in any specific realization. And at time t equals 0, I take a sample exactly as I've showed you before over a length of 1,000 meters. I discretize that, I take a sample, and then I prepare my linear fit to that. And of course, at t equals 0, the average correlation is 1 because the linear fit that's fitted onto the C state at that time. And then I propagate the C using higher order spectral method. And at the same time, I propagate my linear prediction. I just move forward in time in the linear prediction, and then I compare the correlation between the signals. And after 30 seconds, we see the correlation has fallen for in the best case, the least steep case, to around 0.9, and in the steepest case to around 0.5. By the time we reach 90 seconds, the correlations for the steeper cases are almost, I mean, they're abysmal. I wouldn't want to predict anything this way. And even for the least steep case, we notice nonlinear effects are starting to accumulate on these longer timescales. So of course, real waves are nonlinear, and the linear forecast or linear prediction, while initially quite okay, is failing to keep up with what's going on in the simulated nonlinear C. So again, apologies to the experts, and maybe there are some students or some other people that aren't familiar with the techniques. I'll just quickly go through 2 toy examples before I go on to the water wave problem. And the first toy example is this perturbed simple harmonic oscillator with a small parameter epsilon. And I want to use what's in fluid dynamics is a classical idea, namely to expand x in terms of an asymptotic expansion in epsilon in this small parameter. So at lowest order, I set epsilon equal to 0. I have the harmonic oscillator with solutions plus minus e to the plus minus it. At the next order, namely order epsilon, the first order solution comes in as an inhomogeneous forcing. So this is exactly the technique that Stokes pioneered in the 1840s, and that was then developed by Poincaré and others and really got a lot of use in fluid dynamics. So we get this nonlinear forcing term on our simple harmonic oscillator, or we get a forcing term, sorry, it's an inhomogeneity on our simple harmonic oscillator, and we resolve the square. And well, you can solve this. It's very simple by your favorite method. And we see, okay, homogeneous solutions occur here, and then here are all of the inhomogeneous solutions. Okay, so far so good. So we teach our undergraduates this. Let's make a small modification. I've now increased the power to 3, and cosmetically nothing changes at the lowest order. In fact, nothing changes at all at the lowest order. Even at order epsilon, it seems like there's only a 3 here, so quite innocuous. And I expand the power of 3, and okay. And this is the point when the undergraduates need to be a bit careful, because when you go to solve this, you notice something tricky is happening. Namely, you've got your free solutions, so the solutions to the homogeneous problem, but there are these forcing terms that have the same character. Of course, everybody recognizes this is a problem with resonance. So if a forcing has the same form as a free solution, then we notice that we get a secular growth. We get a growth with T because this is a resonantly forced oscillator. Okay, so what does this have to do with the water wave problem? I won't go into many details, but here is the water wave problem for irrotational, inviscid, incompressible flow written in terms of a velocity potential phi, such that gradient of phi is the fluid velocity field and a free surface elevation zeta. So we've got a Laplace equation and two boundary conditions at the surface, and in deep water, I can use a decay condition on the velocity potential. And effectively, Stokes' idea, which I mentioned previously from the 1840s, was to say, let's do exactly this kind of perturbation expansion. And at leading order, that effectively means canceling out all of the nonlinear terms. So it's quite a brutal procedure. You get a Laplace equation and then a combined linear boundary condition for phi on the linear boundary z equals 0. And you find, if you do some algebra, that the solutions have this character. So e to the plus minus I kx minus omega t, which again is similar to the solutions of the ODE that we saw before. The difference here is that we allow for a continuum. So any kind of k, provided that k and omega fulfill a dispersion relation that is imposed by the water wave problem. So any kind of k's are legitimate k's as long as the omegas match. So at this stage, what one should do is plug this solution into the order epsilon problem, so the quadratic nonlinearity problem, and then resolve that, and then again plug in everything to the order epsilon squared problem with cubic nonlinearity. But I'll show you only the main results because the algebra is quite, well, it's quite lengthy. So in quadratic nonlinearity, what we need is, we've got the products of exponentials give us sums of two wave numbers. So k1 plus k2 should equal, say, a k3. But then we notice that the frequencies also need to match. Omega 1 plus omega 2 also needs to be equal to omega 3. And that needs to be valid for the dispersion relation of our system. In this case, the linear deep water dispersion relation, which tells us that this can't possibly be satisfied. This is why when you do the water wave problem to second order, actually nothing interesting happens. At third order, however, the situation changes dramatically. And this is the realization that was essentially behind the work of Phillips and others in the 1960s, who saw at third order, you start to get resonant interaction. Because not only can the wave numbers match, but for matching wave numbers, the frequencies can match as well. So you have resonant forcing in the water wave problem associated with cubic nonlinearity. And in particular, this cubic nonlinearity, which always involves interaction between four waves, so it's a quartet interaction, includes the special cases of the self-interaction of one wave with itself, because Ka plus Ka is Ka plus Ka, and one wave with another wave, because again, Ka plus Kb is Ka plus Kb. The first one, by the way, is exactly Stokes' result, and I'll say a little bit more about that in a minute or two. So I've swept some details under the rug because the perturbation theory itself is quite ugly. But I can show you where these things are encapsulated for the water wave problem. And one very, very compact way to capture what I've just showed you, namely the resonant effects at third order in the deep water water wave problem, is what's called the Zechariah equation. So I don't want to go into huge amounts of detail here, but effectively, this delta, this is a Kronecker delta function, and it meaning it measures when I have resonance between the wave numbers. If this sum of four waves adds up to 0, then I have a contribution, otherwise no. So my wave numbers need to be in resonance. And I have a detuning factor right here, a delta, over the frequencies, which again gives me a major contribution when the frequencies are in or very close to resonance. I've got this is cubically nonlinear, as we can see by the three complex amplitudes on the right-hand side. And there's a kernel term which encapsulates, let's say, all of the specific information about the water wave problem. And the relationship between these complex amplitudes and our free surface elevation is given to lowest order by this expression right here. So a few things about this equation. Again, I don't want to go into huge amounts of detail, but the expression that you see here might look suspiciously familiar. Something similar occurred on the first slide that we had about linear forecasting. Namely, if you sum up these two things, you see this, it actually looks like these are the Fourier amplitudes. And in fact, that's completely correct. The Zechariah equation can be derived from the water wave problem by Fourier transforming, then taking everything to third order and eliminating some certain non-essential, non-resonant contributions where the complex amplitudes are effectively related to the Fourier transform of the free surface and the Fourier transform of the potential at the free surface. And you can reconstruct the free surface elevation zeta in terms of these guys. The difference between this and the linear forecast that I showed you before is that now the BNs are evolving in time according to this system of nonlinear evolution equations. So in principle, we could evolve our waves by solving this system. But it's a bit complex and it's a bit antithetical to the direction that I want to go in this talk. In fact, I'd like to highlight some of the main qualitative features of nonlinear waves. And the first one, found by Stokes in 1847, is that as you go to third order, what at linear order is linear dispersion. So K and omega are related just by omega squared is GK, becomes this corrected expression where the dispersion relation, so omega, still the same linear dispersion relation that we had before, is corrected on account of the wave amplitude A. What this means is that nonlinear waves, waves with finite amplitude, travel faster, and they travel faster the higher the wave is than a linear wave. And this is just it's kind of an innocuous animation. Blue is a linear wave, red is the Stokes corrected or nonlinear wave. And indeed, okay, you put in this correction for a finite amplitude. These waves are going faster. Not very exciting. It took a long time from Stokes until Longit, Higgins, and Phillips finally figured out how you could do this for the mutual correction of waves. Because in a real sea, you don't have one wave train. You've got, well, maybe 2 or 3, or usually many, many wave trains. Whether it's a continuum or whether you have many discrete wave trains, we can discuss later. But Longit, Higgins, and Phillips finally managed, again via perturbation theory, to recover Stokes' results. So linear dispersion means that two waves with, say, wave number Ka and Kb don't feel one another. They don't know that the other wave is there because linear superposition holds. At third order, we find that the wave numbers, or the two modes, correct one another. They correct one another in terms of this corrected frequency, the first part of which is the self-correction. This is the Stokes correction that we just saw before, epsilon being A times K. And they correct one another in an asymmetric fashion via these coefficients here. And that asymmetric fashion depends on which wave is longer. So the longer wave corrects the frequency of the shorter wave a lot, but not vice versa. And what this means is that although for each individual wave, again, nonlinear dispersion really looks like almost a phase shift. Once you start to get superposition in there, that's the lowermost panel here in this video, the picture becomes more complicated. Okay. Now it turns out that these two effects, which are two of the most important effects of nonlinearity, can be extracted from the Zechariah equation. if we assume that there's no energy exchange or neglect the energy exchange among modes, we can in fact integrate the Zechariah equation or the discretized Zechariah equation, which I showed you explicitly, to give a correction. So here's omega n, the corrected or nonlinearly corrected frequency, is equal to the linear frequency little omega n, and then some stuff here on the right-hand side. The BPs are basically the Fourier amplitudes with a scaling, and the kernels, which can be very complicated, in this simple unidirectional deep water case, reduce to these expressions that you have here. So if I've got two wave numbers, k or n and p, the kernels are np squared over 4 pi squared if p is less than n, and with the squared on the other one if p is greater than or equal to n. So this is an algebraic correction that we can extract from the Zechariah equation, and which gives us, if you restrict to one mode, Stokes correction. It gives us, if you restrict to two modes, the results of Longet-Higgins and Phillips. And moreover, if you have an arbitrary number of modes, it still gives you a usable correction. And I'll show you what I mean by usable. This is a slide that you've seen before. It's the slide where, I said, okay, we take our Fourier transform of our discretized signal, I add linear dispersion in this fashion, and I get a linear forecast. Now I can change this in a very slight way by replacing our linear dispersion, which is just essentially square root of g km, by nonlinear dispersion. And the beautiful thing about this is it's an algebraic correction. I don't need to solve anything. The nonlinear frequency depends only on the wave numbers and on the Fourier amplitudes, which I've already calculated. For good measure, I should replace the subscript L for linear forecast by S for Stokes corrected forecast. But otherwise, I don't need to make any changes. I don't need to solve any equations. I've only incorporated the effects of nonlinear dispersion into this into this simple form. So, of course, I should say something about what we're neglecting. And what you see here in these three panels, so panel 1, 2, and 3, are records from a wave flume. And here are the Fourier amplitude spectra. And indeed, you see that the energy exchange, which a few slides ago I said I assume that it's not happening, is of course happening. This is a very dramatic example because I've got one dominant mode right here, which you can see is the big spike in the Fourier amplitude spectrum for the first panel, and two side bands next to it. And we find that as the wave propagates down the tank, the side bands in fact grow. Here, the sideband amplitudes have grown at the expense of this dominant mode. That energy exchange is constantly happening in real water waves, but we need to assume the Fourier amplitude spectrum remains constant. Otherwise, of course, there's something happening in space and in time, and then suddenly I need to solve some evolution equations. But the lovely thing about this algebraic correction is it's very, very easy to compute, so you can drop it in and find a correction. For short times, that correction looks like a phase shift. So here again, we're seeing in red nonlinear dispersion, in blue linear dispersion. But for longer times, the differential phase shifts, let's say the differential effects of nonlinear corrections on the different modes, start to change the signal in a very dramatic fashion. And so you can ask, how good is this Stokes corrected forecast? And okay, I'm showing you averaged correlation. And again, I've used, just to remind you, 50 realizations generated by the higher order spectral method with 3 different average steepnesses. And for the connoisseurs among you, I'll say that these are drawn from a John swap spectrum. So I've got an epsilon of 0.1, 0.15, and 0.2. And the blue curves, or blue, well, let's say blue lines here that you see, are exactly the ones from the previous figure. So the blue is the linear result that I've shown you previously, where we said at 90 seconds, the correlation between the linear forecast and the synthetically generated C is not great, say. The red curves that we see here have only one change made to them, namely I've replaced linear dispersion by nonlinear dispersion. And indeed, we see that this change is dramatic. Although the actual C includes energy exchange up to higher than third order, although it includes bound modes, about which I'll say a little bit in a minute, the prediction that I'm able to make using this algebraic Stokes correction remains very, very good. Much better than, so even for the severest C states, the prediction is almost as good as the linear prediction for the least severe Cs. So this is a good idea that, at least for synthetic C states, we're doing quite well. I'll also show you one figure where we compared with experimental results in a wave flume. Again, I won't get into the details too much. Suffice it to say that, again, we've generated, or these are experimentally generated waves with steepness around 0.2, so fairly steep waves, where I've taken measurements from a single probe to initiate a linear forecast, the red line, and a nonlinear forecast, the yellow line. And we see as the waves move down the tank, so this is about 3 meters or 3.5 meters from the first probe. This is about 6 meters or 6.5, and this is almost 10 meters. The linear forecast starts to diverge markedly, whereas our nonlinear forecast captures the behavior of these actual waves in a much, much better fashion. Okay. So this is, in some sense, what we know so far, and I hope that the picture seems optimistic to you. And I'd like to leave it on a slightly, maybe less optimistic note, because there are some open questions, there are some open issues that I'm particularly interested in. And one of them is, what about the role of bound modes? So I said that the most important aspect or feature of nonlinearity is this correction to dispersion. But if you've done water waves for a while, or you've looked at maybe other nonlinear waves, you'll be aware that nonlinearity also changes wave shape. So hitherto, I've been acting as if all of my waves are sinusoids, albeit maybe sinusoids with a corrected frequency. But as it happens, real waves aren't sinusoids. Real waves, nonlinear waves, are sharper at the crests and flatter at the troughs. And this is a feature that comes about in the weakly nonlinear description of water waves because of something called bound modes. So when you go to second and third order, not only do you get these or at third order, you start to get these corrections to the dispersion relation, but you start to also find other harmonic constituents. In this case, if I've got a wave with mode K, I start to find modes 2K appearing in my Fourier solution. And the peculiar characteristic of those modes is that they're bound modes. Now, what do I mean by that? In the picture, I'm showing you a Fourier amplitude spectrum where I've got a single dominant mode at, say, K is 0.2 and a bound mode at K 0.4. Now, there exist steady waves with such bound modes where the bound modes move at the speed of the free waves. That means that I've got a steady wave, which is sharper at the crests and flatter at the troughs, but which propagates without change of form. But of course, the Fourier description is insensitive to that. If I simply take this kind of Fourier description, well, the things that I've showed you hitherto would assume that this is a mode at k0.2, it propagates at square root gk, and this is a mode at k0.4, it also propagates at square root gk. And what that leads to is a, let's say, a split in how the actual waves are moving. The actual waves being here the blue waves, the steady, let's say, Stokes wave solution, and what our Fourier description thinks should be happening. Namely, what we find, again, because the waves are dispersive, is that the waveform, on account of these two modes, the free mode and the bound mode, the waveform distorts periodically. So this, it turns out, is a bit of a problem. It's not so much a problem if we know exactly what the free modes are, because again, our Zechariah formulation is very powerful. We can recover from it exactly what the bound modes should be if I know what the free modes, the complex BIs, which correspond to the Fourier amplitudes of a free C, are. So in particular, if I know what a free wave state looks like, I can add the bound modes analytically. I can do it using such a somewhat unwieldy, but nevertheless simple to evaluate expression. And as long as I'm only doing synthetic forecasting, I also don't have a problem, because I can generate the free waves and the bound waves separately. I can propagate the free waves only as they should, and then I can add the bound modes later on, because I know the bound modes, they're trapped. They're propagating it at the same velocities as the free modes. The problem is bigger when I'm doing actual measurements. And this is something that we're actively working on right now. Namely, if I've got a single snapshot, like here in a wave flume, I can't distinguish the free and the bound modes. If I had an ensemble of measurements, so I were able to take many, many measurements in space and time, and I were able to plot where the energy lies, I could identify curves in this case, K and omega. So this is why we require space and time. I could plot a wave number frequency spectrum, and I could identify the free mode energy, and then over here, the first harmonic bound mode energy. But of course, in deterministic wave forecasting, we don't have such an ensemble. So if we could remove the bound modes accurately, we could propagate the free modes and add the bound modes back. But removing the bound modes accurately is still a bit of a problem. Some approximations exist, and it's something that we're working on currently. So I think my 50 minutes are very nearly up. So I'll just end with a few problems, questions, and some maybe some ideas for future work, some of which is ongoing. One thing that I mentioned already, can we effectively treat these bound modes? So can we isolate in an easy to use and fast fashion what the bound mode contributions are to create more accurate forecasts? And I emphasize fast because remember, deterministic wave forecasting is operating on a time scale of maybe tens or hundreds of seconds. So I can't be spending lots and lots of time crunching numbers and solving systems. I need a forecast now so that I can tell my wave energy converter how to adjust its damping coefficient, so I can tell my ship what kinds of motions are going to occur. One thing that I haven't talked about yet are finite depth effects. So a lot of the things that I've presented can work in finite depth, but there are some subtleties that you get into, and this is something we're actively looking into. Another thing is directional wave fields. Of course, there's an ambiguity in the Fourier description if I've got counter-propagating waves, but as long as I have directional wave fields with a spread of waves between, say, minus pi and pi, which would be usual in most Cs, you can treat this effectively using the tools that I've outlined in the talk hitherto. And then the two last big topics, which I know less about, but I would be very, very happy to to learn more about, are uncertainty in measurements. and unresolved physics. So lots of things, of course, aren't taken into account here, including the fact that the measurement itself is imperfect, the fact that there's lots of things happening in the sea that aren't accounted for in the simple kind of models that I've presented. Of course, we've got wave breaking, we've got a continuous wind input, we may have currents and other things that confound the picture. But okay, I think that's enough for now. There are a few references that I can leave up in case anybody is interested in reading more about the things that I've talked about. And otherwise, I'd be happy to open the floor to questions.
Thank you very much. Thank you. Very interesting. Yeah, very interesting presentation. Very interesting results. First, I'll ask our participants any questions, please, or any comments, please. Any questions from our participants? Right. I have several questions. Some of them you answered at the very last slide, discussing the future work. Yeah, indeed, it's very exciting. And but there could be two formulations of this problem. So I'm trying to understand which of them could be kind of better, or they both one or another could be used in different for different conditions. First of all, first option for first formulation is to predict waves if we now if we measure waves at some distance from the site, say. So the independently what is in that site. So we just kind of pure mathematician concerning about the waves which come to that place. Other formulation, it could be, but it's I didn't see it properly done. Other formulation is that we are not concerned with the exact waves coming or exact forecast, but we are concerned with kind of estimates. What the say highest wave could be if could come from that measured conditions, and in particular that is the as I remember the that directional wave spectrum. If we do not impose it, but if we measure it through several buoys, then it's kind of complicated to even each buoy has several degrees of freedom, and you have several buoys, but it's difficult to measure accurately what that incoming field is. So, but if we are not concerned with exact waves, but we want to estimate the highest, then it's okay if we use the data which is not kind of certain. We know only some relations between the input data, and then we can estimate the highest wave, for example. If it's, so, what's your opinion on that?
Oh, okay. So I think there I see thank you for the question and interesting comments. I see several possible ways to address this. So one, because you mentioned arrays of buoys and attempting to recover what exactly the wave field even from a single buoy is, which is not straightforward, and the buoy response is it itself has an effect on what's recorded, and so on. So now I don't pretend to be an expert on this, but there is some literature about which is effectively trying to use data assimilation techniques from arrays of buoys to reconstruct wave fields. And I think there is a recent paper by Dick Yu and co-workers in JFM in 2018. I think first author is Lee, and then a number of co-authors, and then Dick Yu, who look at data assimilation for using spatiotemporal measurements for the purposes of deterministic wave forecasting. Now the other issue that you raised, and which one can see them as the same issue, but of course there's also the question, if we're not interested in an exact wave by wave record, or maybe not in the details of an exact wave by wave record, but only in, let's say, what might be the biggest crest or the biggest trough that could come out of a specific sea state. Now, okay, I'm going to leave aside the possibility of doing it in a phase averaged way. I mean, we have well-developed, say, kinetic equations for how waves should propagate in if we weren't concerned about individual wave phases. It's a very interesting question. And I wonder how much we could recover if we added, say, a bit of noise into the signal using the methodology that I outlined. If you add a bit of noise into the signal, or even do some, you could simulate it via some high pass or low pass filtering. Say you cut out, say, all of the waves that aren't of interest except maybe the biggest, and then see how does this evolve. How on average are you going to be able to capture the main features over short time scales of a few minutes? This could be something quite interesting to look at. I don't know if it's so easy to do with actual buoy data. I mean, again, my instinct would be to try to do it via synthetic data first, because you can control everything. With the buoy data, I don't know enough about how much the buoy itself smooths the wave record. And I think there's some recent work by Ton Vandenbremer and collaborators who looked at uncertainties in buoy measurements. For example.
Okay.
But although, granted, I saw a question by Davide in the chat that I should try to address. I mean, okay, of the wave frequency depends on ys. Does it depend on y at any time or at time t equals 0? So, Davide, yes, thank you for the question. So the in fact, the nonlinear correction depends on y at any time in reality. Because it's constantly, so energy is constantly being exchanged among the modes, so the y's are constantly changing, which constantly changes the frequency correction. But in some sense, the trick that we happened upon was to say, let's pretend that it depends on the y only at time t equals 0, and assume that we can use this at least for a moderate time span. So assume there's no energy exchange. The initial y's, that's all the y's that we know about. So I sense them, and that's it. Assume that dominates, or that can give us the frequency correction. How good will that be? And it turns out it's fairly good. It's not reality. In reality, of course, you have, the reduced Zechariah equation in this, or in fact the full water wave equations. So in reality, the frequency correction is always changing. Okay, yeah, thanks. Sorry, I'm happy to share the slides again, but I realize when I do that I can't see the chat. So if there are other questions.
Any other questions? Any other questions by chat, or
so
you can unmute your microphone.
I think Davide doesn't have a microphone, he wrote previously. Please.
No, I do not have a microphone, he said.
What's the error we have in not considering the bound modes? In deep water, it's very small. Yeah, in deep water, the error is very modest, and in fact, when we tried filtering out the bound modes using some approximations due to Fedele and coworkers, we found that it wasn't worthwhile. So what we haven't considered, yes, Alberto, yes, thank you for the comment. So this also depends on how broad the initial spectrum is. If we've got a very narrow initial spectrum, the bound modes are very distinct. You start to see them changing the wave field dramatically, and it's almost impossible to recover what with let's say if you try to experimentally generate a Stokes wave, so sharp crests, flat troughs, and then just use our methodology without correct bound modes, it disintegrates immediately. Basically, as I was indicating, I can go back to this video here, like in this video here, but of course much more dramatically, where you see there's a disintegration in the wave field that comes about because the bound modes aren't resolved correctly. Now, so we're talking the difference between the red and the blue curves in the animation. And that's very, very noticeable for narrow spectra. For broad spectra, it's not such a big problem. Now, of course, as the depth gets smaller, bound modes play a bigger role. And so this is one of the trickier bits as we try to tackle the finite depth problem. Namely, we need to be more, so we need to really develop a good methodology for well, getting rid of them first and then adding them back in, which is adding them in is easier, but getting rid of them is the tricky bit. Sorry, we're now over time, so
yeah, it's okay. Any could be last questions? Yeah. Okay, so Raphael, thank you very much. There is the
okay. Okay, no, please, thank you for the invitation. And
sorry, it's my problem. So then, thank you very much for your very nice presentation and many ideas how to do this. And I see that you are on the long way to the goal, and there are many things to be solved and resolved. So the yeah, okay. So some people are typing. So Emilian is typing. Okay. And then, yeah, just thank you. So then I stop recording first. Stop recording.